My name is Mariano Zaron, and in this video, we're going to see how we can approximate the derivative of a given function f. So in general, when one is using some approximating technique, if one takes the derivative of the approximator, that tends to be a bad approximator for the derivative of the function. Now that is not the case with Chebyshev techniques, which makes it actually quite unique. And now we're going to see how that is the case. So the situation that we have, as I said, is you've got a function f, a pricing function, for example, and we want to approximate it. We already know that you can build Chebyshev objects for that. Really good approximators. This is Pn. Not only are they easy to build, that is to calibrate, but also very easy to compute. We use the barycentric interpolation formula, off you go quickly, and it's also numerically stable. Now let's assume that we also are interested in approximating its derivative. What in finance they call the Greek, basically, and that's going to be f prime. So of course, one thing that we could do is build an object for f prime. That is a Chebyshev object. So here I've denoted that Chebyshev object by Qn. And of course, we would have its corresponding expression in terms of Chebyshev polynomials with these di coefficients, and also in terms of Lagrange polynomials, where we have these wi coefficients. So of course, that's a route that you can follow. And we know that we would have all the nice properties that you usually have for Chebyshev polynomials. However, that involves having to evaluate f prime. And it may be that you don't have access to f prime, or simply that f prime may take a bit of time to compute. And even when you have to evaluate it only 10 times, and even if f prime is not even that slow, we can take advantage of the fact that taking the derivative of Pn is a good approximator to f prime, because as we will see in a second, computing the derivative of p prime is really straightforward, and hence you avoid having to build this object, even when the building of this object may not be that complicated. So now let's dive into how we can compute very quickly Pn prime, and at the end I'll justify why Pn prime is a good approximator to f prime, which, as I said, is a very unique property of Chebyshev spectral methods. So Pn prime. Notice that Pn of x is a polynomial of degree at most n. That's just how it's been defined. If we take the derivative of it, we again have a polynomial. And of course, trivially, it also has a degree at most n. The important thing about that is that if we are to build a Chebyshev object for Pn prime, we know that the only thing that we need for that is evaluate it on the Chebyshev points xi. And if we define vi prime to be the value of Pn prime at xi, what we know is that the Chebyshev object is the unique polynomial of degree at most n that on Chebyshev points takes these values. That's by definition. But we know that there's only one unique polynomial with that condition, and we know that there's another polynomial, Pn prime, that has that same condition. Hence, the Chebyshev object, which I'm going to denote by Chev of Pn prime, that is equal to Pn prime. So in order to evaluate Pn prime on any point, the only thing that you need to do is evaluate its Chebyshev object. And for that, you need the barycentric interpolation formula and these values vi prime. By the way, anybody who hasn't seen or is not familiar with barycentric interpolation formula, we have a whole video dedicated to it. So go and see it, because that's essential to the theory that we use to approximate pricing functions f. Okay, so it seems that in order to be able to evaluate Pn prime, the only thing that we need are the vi primes. Now, how do we obtain these? Notice that Pn prime of xi is using this definition over here, the same as taking this linear combination. I'm going to put here j's. J at xi prime of Lj. So Lj are the Lagrange polynomials. So basically what we need is find what the derivative of the Lagrange polynomials is at each of the Chebyshev points. Now, Lagrange polynomials have a really nice property when it comes to computing their derivatives at these xi points, because Lj prime at xi happens to be only mu j over mu I xi minus xj if I is different from j, and it's xj 1 minus xj squared if I is equal to j, where mu I is equal to minus 1 to the I if I is different from 0 or n, and it's equal 0.5 times minus 1 to the I when I is equal to 0 or n. So take a look at this expression over here. We've got mu j, so the mu i's are simply these coefficients, trivial, and the xi's are the Chebyshev points, for which we've got an expression, so trivial. Computing these values here is completely straightforward. And if we define a matrix dij to be these values, from this expression, we get that v prime, which is the set of these values over here, is equal to d times v, where v are these coefficients over here that we started off with. We started with f, for which we've computed a Chebyshev object. So we've got these vi's. Computing this matrix D is straightforward, as can be seen by this expression over here. Hence, computing these v primes is completely straightforward. And once we have those v primes, you can use the barycentric interpolation formula in order to be able to compute Pn prime of x. So that's all we need to have access to the derivative of Pn. That's all. This is for the derivative of first order. What would happen if we were interested in further orders? The only thing that you need to do, for example, let's say they were interested in the mth derivative of Pn, the only thing that you need are, again, the values. This is applying the same argument that I applied above here. The values at Chebyshev points, which we're going to define by vi to the m, for example, and following the same argument that we followed for the first derivative of Pn, you have that v to the m, which is the set of these coefficients, is equal to applying dm times to the set of values that you started off with, v. So it is really straightforward to come up with a way of computing the derivatives of Pn of x. Now, as I said at the beginning, this, in principle, or in a more general setting, let's assume that this wasn't necessarily Chebyshev approximation, but it was some other form of approximation. Computing the derivative of the approximate is not necessarily the way to go forward. However, in our case, it is. And that is justified by the following theorem, which really lies at the core of Chebyshev approximation theory. And you'll be able to recognize this theorem, maybe not in its with a full statement, but you'll be able to recognize it because it's a theorem that we've already spoken about many, many times. And it says the following. Let's assume that f is a function, your pricing function, and we assume that it's analytic. So basically that means that you can always approximate every point of f in its domain by its Taylor series, that it converges and converges to the same value that f has at that point. So if f is analytic, what we know is that Pn, so this object here, Chebyshev object, converges to f with respect to the supremum norm, that is the maximum error between these two things. This converges to 0 as n tends to infinity, and it converges exponentially. And this, of course, as you already know, lies at the core of Chebyshev approximation theory and the applications that we're interested in. But moreover, another thing that we have is that the nth derivative of Pn approximates the nth derivative of f exponentially as n tends to infinity. So essentially you've got the same result for the original function and its Chebyshev object. And if you take Chebyshev objects, original function, and start calculating the derivatives of each of them, you still have this approximation. So we've seen the theory of how we can compute derivatives using Chebyshev objects. Now let's take a look at a couple of examples and see what the accuracy is of these objects and how quickly we can compute them. So I've prepared this code for you. First, I'm going to start with a very simple function, the sine function, and we know its derivatives. The first order derivative, it's cosine. The second order derivative is minus sine. These examples are one-dimensional. And I'm going to approximate, or I'm going to build a Chebyshev object between minus 10 and 10. So as you are already familiar from what I just explained, the idea is that you only build one Chebyshev object, and you build it for the original function. With that, and with a matrix D that is very easy to compute, you have all the information that you need in order to quickly and stably evaluate all the derivatives that you want. And the only reason why I've written here the first and second derivative is for comparison purposes, to compute the error of the approximating object. So let's run this code and see what we have. So here we've got the original function. On the right-hand side, we've got the error of the Chebyshev object that we've built with respect to the original function. We've computed the maximum relative error here, which is of the order of 10 to the minus 5. So perfect. And then we've got the first derivative. So this is the function that we want to approximate. And on the right-hand side is the error that the original Chebyshev object makes when evaluating not the Chebyshev object, not the approximant of the original function, but its approximant to the first derivative of the original function. And we see that the maximum relative error is again of the order of 10 to the minus 5. When it comes to the second derivative, as we know, no extra effort in order to come up with all the information needed in order to evaluate it. And again, we come up with a really good approximation, in this case, again, of the order of 10 to the minus 5. Great. Let's give it a more realistic example to deal with. Again, we're going to use Black-Scholes pricing function. We have to change the domain of approximation to, let's say, 50 and 115. And let's run it again. This time, we're going to be approximating not only the original pricing function, Black-Scholes, but also its Greeks, without, again, having to build any objects for the Greeks. And what kind of accuracy do we get? So the original function is this one. Accuracy 10 to the minus 11. Perfect. Then comes the first derivative, which is the delta. And we can approximate it to 10 to the minus 10. Really good. This is, again, using just one object, the one that we built for the original function. We want to approximate the gamma, which is the second derivative that we see below. We have a relative error, maximum relative error of 10 to the minus 8. So all of them with great accuracy. And again, the evaluation of that object is just as quick, regardless of whether you want to evaluate its approximant to the original function or to any of the Greeks. So this was for one-dimensional examples. And all the theory that I mentioned before is relevant as an illustration. The way that I gave it is for one dimension, but it also works for high dimensions. And let's take a look at how that looks when we take high dimensional functions. Again, for illustration purposes, we're going to keep it at 2 dimensions. And I'm going to be using Black-Scholes and its Greeks up to second order. So we have the delta, we've got the gamma, we've got vega, we've got vomma, and we've got vanna. Perfect. Let's build an object for the original function, specify that we want approximants or approximators up to order 2, and evaluate that object in each corresponding case and see what we obtain. So here we've got the surface for the original function, as you can see, and an error of around 10 to the minus 7. Then we've got the delta. Let's wait for it to finish running. I'm going to go slightly up. Then we've got the delta above, over here, at the top, with an error of 10 to the minus 6. Then we've got the vega, 10 to the minus 5, gamma, which is second order, 10 to the minus 4, vomma, which is second order with respect to the second variable, which is volatility, 10 to the minus 3, and then vanna, 10 to the minus 4, which is the cross derivative. That is derivative with respect to spot, followed by derivative with respect to volatility. So great. You can also do a really good job. let's give it a different function that I've cooked up here. It's just a made-up function so that you see it working with something completely different. Here is just a multiplication of a cosine with respect to the first variable, exponential with respect to the second variable, with some powers inside. Let's change the domain of approximation so that it makes sense, considering the kind of function that we have. Again, we're going to be running the same kind of test. So building a mocax object or a Chebyshev object for the original function, specifying that we want the information in order to approximate the derivatives as well, and using them in order to evaluate or approximate the derivatives. And what do we get? So we get something very similar to what we had before, as expected. So we've got the original function that looks like this sort of saddle with an error of 10 to the minus 6. Then the delta, which, well, I've kept the names for the Greeks here, but of course the delta is the partial with respect to the first variable, and that is 10 to the minus 6. Then vega, which is the partial with respect to the second variable, 10 to the minus 5. Gamma, which is the second order partial with respect to the first variable, 10 to the minus 6. Bomma, which is second order with respect to the second variable, 10 to the minus 4. And the cross derivative, which is Vanna, 10 to the minus 5. So great accuracy. And again, the important thing to bear in mind is you can always build Chebyshev objects for each and one of those functions, but you don't need to. You can build it for the original function, then the rest are basically for free from all that I explained before in the theory. So basically, in summary, what you have is function f, its derivative. You're interested in approximating the derivative of f. F already has a Chebyshev object that you've built for it. Very easy to compute the derivative of Pn. Basically, boils down to computing these coefficients, the ones for the matrix. Use the barycentric interpolation formula for these values over here. So that's very quick. And the reason why we can justify using this approach is because this theorem says that not only does a Chebyshev object approximate f exponentially as n tends to infinity, but also the corresponding derivatives of Pn approximate the derivatives of f exponentially as n tends to infinity. So please get in contact with us if you've got any questions regarding this or anything else, and see you next time.